Okay, great. Yeah, thank you very much for the invitation. I've always been very curious about this group, I have to say, so it's nice to be here at least virtually. So what I will tell you today is a bit about ways for searching for dark energy off the beaten track, which are not the usual ones in cosmology. And so this sort of connects to what Raoul said about going in different ways to understand fundamental physics, broadly speaking. Okay, so there will be 2 + 1 parts to this talk. In the first part, I will talk about what I call direct detection of dark energy here on Earth. In the second part, I will take a more cosmology point of view and tell you about consistency test of lambda CDM in a way which is as model agnostic as possible, and what we can learn about dark energy at early times, where by early I mean pre-recombination. In the third part, I will talk about new ways to search for light particles, which might be related to either dark energy or dark matter or neither, using black hole shadows and asteroids and planets. So just as a note, in order to highlight the contribution of early career researchers, when I show my collaborators, if their name is in blue, this is a student, master or PhD student, and in red, it's a postdoc. Since I want to talk about how to search for dark energy off the beaten track, let me first say what, in my opinion, is the beaten track. I'm going to simplify a bit and be a bit provocative, but the beaten track is looking for gravitational signatures of dark energy. This means that we look for the effect of dark energy's energy density on either the background expansion or the growth of structure, as probed by standard observations. By standard, I mean, for example, supernovae, which is how we first discovered dark energy through the background expansion, or large-scale structure, galaxy clustering and redshift space distortions, which measure either the expansion rate or the growth of structure. And there's a lot of focus in the field on nailing down the equation of state of dark energy. So the ratio between its pressure and energy density. This is sort of, simplifying quite a lot. That's sort of the beaten track. A lot of effort is going in this direction. But what I want to ask is, can we learn more about dark energy beyond these standard probes? And so in the first part, I will talk about what I call direct detection of dark energy. And what I want to ask here is there anything interesting beyond gravitational signatures of dark energy? Let me draw a parallel with dark matter. So we know dark matter exists since at least 1920, although only in 1970 we became convinced about it. And we really first discovered dark matter through gravitational interactions. But nowadays, in 2020, the state of the art in searching for dark matter is actually to go for non-gravitational interactions. So in particle physics talks, you might have seen this very schematic Feynman diagram. The way to read it is you can read it in different directions and you get different search channels for dark matter. For example, if I read it from bottom to top, what you get is as time goes by, you see dark matter scattering off normal matter and you look for the products of this scattering. You look for recoil of normal matter off something invisible. And that's called dark matter direct detection. And there are many big underground labs under mountains which are looking for dark matter direct detection signals. I can read this diagram from right to left, and then you get dark matter annihilating or decaying into visible matter. And you look for the products of this decay, which can be high energy cosmic rays, neutrinos, photons. Or you can read it from left to right, and you get production of dark matter from normal matter. And this can be, for example, collider production. And this is sort of the three-pronged approach towards detecting dark matter. Okay, this is really the state of the art today. That's what we're going after, to understand the particle nature of dark matter. For this talk, I'm going to focus on this direct detection approach. But of course, one can also think about these other detection channels for dark energy. So the question is, does it even make sense to think about this diagram for dark energy instead? Are there non-gravitational signatures we can go after? And that's something I've been thinking about, on and off for the past 2 years. And I should say, this was inspired by a person who was in this group. This person is Fergus Simpson. He was a postdoc in Licha's group a few years ago. But in this very nice paper he had about 10 years ago, there was this very nice table with the typical cross-section for interactions between the various components we know, okay? Now, these numbers in purple are not totally correct, it turns out, but it was very intriguing that it looks like you can have large interactions. These are in, the units here are barns, so about 10 to the minus 25 centimeters squared. You can in principle have large interactions between dark energy and electrons, okay? Again, this number is wrong, it's not totally right, but it's intriguing that, you know, there's nothing forbidding these interactions, at least at the cosmological level. So I started thinking more about these interactions, and more generally, the question one has to ask is, can dark energy and visible matter talk to each other in the first place? Is there anything forbidding this? And in fact, the answer is yes. If dark energy is due to a new degree of freedom, like a new particle, it's typically going to talk to visible matter, unless you find a very good reason why it should not. A good reason means a fundamental symmetry which forbids these interactions. So if dark energy is a new light particle, even if you don't couple it to visible matter at tree level, it's always going to couple a loop level if there's no symmetry forbidding this coupling. Now, this is sort of a curse and a blessing at the same time for two reasons. The reason is, if dark energy is a new particle, it's got to be extremely light. Its mass typically has to be at the Hubble scale or less, so around 10 to the minus 33 eV. And it will typically have gravitational strength coupling to matter. This is a blessing because it means maybe we can hope to detect dark energy by these interactions, but it's also a curse because it leads to long-range fifth forces. So a fifth force of this type, it's a Yukawa type fifth force. This is a curse because we don't see any evidence of fifth forces. There are very, very stringent constraints on fifth forces of essentially any range. The way to get around this is you can either tune your coupling to be extremely weak. This should be much greater than. You can tune this mass scale to be much larger than the Planck scale, or the range to be extremely short. They are not nice. We don't like tuning things by hand. So the way around this is by a so-called screening mechanism. So what we want is a fifth force which dynamically weakens based on the environment. We want a fifth force which weakens in the local universe, where we know that Einstein's gravity works very well. Now, if you look at the expression for a fifth force, you can see there are at least 3 handles you can play around with to tune it. You can play around with the coupling, and that's what we get in the so-called symmetron screening mechanism. You can play around with the inverse square law, and that's typically what happens in the Weinstein mechanism. And I believe in this group meetings, you heard about this from Daniela Sade recently. And you can play around with the chameleon screening mechanism, which plays around with the range of the fifth force. So you want a force which becomes very, very short range in dense environments. And that's the one I'm going to be interested in this talk. So how does chameleon screening work? The name of the game is you want a force which is very long range in space, where you can deviate from GR if you want to explain dark energy, but very short range on Earth. And the way it works is you have a scalar field which no longer responds to the bare potential V of phi, but to an effective potential which depends on an explicit coupling to the local matter density. We see phi couples to rho m. You can see schematically how this works here. The effective mass of your field is essentially given by how steep your potential is around the minimum. Now, when you raise the local matter density, this linear term grows, it becomes steeper, and therefore your field becomes much more massive. So the effective mass of your field typically scales like the density to some power. So this means we can have a field which is very, very light in outer space. It's ultra light on cosmological scales, but it can be heavy enough on local scales, so we hide the effect of a fifth force. So the point here is, if we want dark energy to be a light scalar field, which is the simplest explanation beyond the cosmological constant, we need some sort of screening mechanism. And the next question becomes, can we actually detect screened dark energy on Earth? And this is the question we ask in this recent paper. We ask ourselves, we have these big experiments which are trying to directly detect dark matter. Can we use them to detect dark energy instead? So this was done with my colleagues in Frascati, Paris, Cambridge, and Hawaii. And it was actually covered in many newspapers throughout the world, including in Spain. So let me show you how this works. In order to detect this dark energy scalar, screened dark energy, we need a production mechanism and a detection mechanism. So for production, we consider two possible couplings. These are the most general lowest order couplings you can write between a dark energy scalar and the photon field. The first is an anomalous coupling to the photon field strength tensor, F squared. And the second is a so-called disformal coupling, where you couple derivatives of the field to your energy momentum tensor. So what this does in practice is it allows you to produce dark energy quanta inside very strong magnetic fields. One example is in the sun. Between the radiative zone, the inner zone, and the convective zone, there's a thin shell called the tachocline, where there's a very strong field, about 30 Tesla. And what happens there is you can convert photons into dark energy particles. This can then travel to Earth, and they can interact with visible matter in these big dark matter direct detection experiments. So how does this work? It works exactly through the type of couplings we need for the chameleon mechanism. So here we consider a generalized class of couplings. This is the conformal coupling. You couple to the trace of your energy momentum tensor, which is essentially your matter density. This is the same coupling I showed you before. And you can also have two types of coupling called disformal and kinetic conformal. The details are irrelevant, but the important thing is what they give you is a mechanism which looks very much like the photoelectric mechanism. So you have an electron which absorbs a dark energy particle and then recoils at higher energy. And you can look for the product of this recoil. Why is this interesting from the practical point of view? Well, there's an experiment called Xenon 1 ton. It's under Gran Sasso in Italy, and they are looking for dark matter. And about 1 year ago, in June 2020, they saw an excess event, about 53 more events than expected, at energies of around 2 keV. Okay, the most popular explanation at the time was solar axions. Okay, axions are very light pseudoscalar particles, which can be the dark matter. These are the data points of the Xenon experiment, these black points. The gray curve is the background, and you see here there's a roughly 2-3 sigma excess. Now the solar axion fit is in red. You see, it gives a very, very good fit to the signal, but there's a problem. It's completely excluded by astrophysics at about 20 sigma. The reason is stellar evolution, because if the sun produces enough axions to explain this signal, denser stars like white dwarfs, red giants, and horizontal branch stars are going to produce many, many more axions. They are going to cool very fast and evolve in a way which is not allowed by observations. What if we consider solar chameleons? So these dark energy particles produced in the sun. We get this blue curve, which is a less good fit. It's roughly a 2 sigma fit preferred over the background, but it comes with a huge advantage that it's not excluded by astrophysics. Precisely because of screening, we can arrange our parameters in such a way that we produce these particles in the sun, but not in denser stars. So we evade the problems faced by axions. Okay, so the takeaway message is, even if this is not new physics, honestly, I don't believe this is real. I think it's a fluke. We can use this dark matter experiment to search for dark energy. So what we say, killing 2 birds with 1 stone. And I think it's something which is worth looking more into in the future. And we are thinking a lot in this direction, especially since there will be many upgrades to the Xenon experiment. And there are, at the same time, competing experiments in the US and in China, which are looking at the same region. So if this is a real signature of new physics, we will see it again in the next years at much, much higher significance. And we can start to test, differences between this dark energy signal or axions or whatever other signal you have in mind. So I'll move on to the cosmological part, because now no one has raised the most obvious objection, which is, okay, if I see this signal, I'm seeing it on Earth, how can I know that this is the same particle which is accelerating the universe? Okay, there is no way you can know for sure based on this signal alone. And by the way, let me say the same happens for dark matter. If you see a dark matter signal on Earth in a collider or whatnot, you can never be sure it's the same dark matter which is out there in the universe, okay? What you want to do is look for complementary signatures in other observations. So I know that complementary is a word which is very abused in the field, but trust me, here it's really important. So the question we can ask ourselves is, if dark energy and visible matter talk to each other in a way which is strong enough to explain this signal, what do we expect to see in cosmology? So in this paper 2 years ago with Olga Mena and David Motta and Luca Visinelli, we ask ourselves, let's assume that dark energy and baryons scatter very strongly. is it going to mess up cosmology on linear scales? And the answer is actually very surprisingly no. So we took a very phenomenological approach. What we did is the following. We modified the Boltzmann equations for baryons and dark energy. And we modified it in such a way that you can get scattering between the two. And the terms which describe the scattering are in red. And you see there's this term which depends on 1 plus the dark energy equation of state and the ratio between the dark energy and baryon densities. And this is here because of energy momentum conservation. It's very similar to this term over here for Thomson scattering. So we play the following thought experiment. This interaction depends on a cross-section between baryons and dark energy. Let's crank up this cross-section to a value which is huge and totally unrealistic, which is the Thomson cross-section. This is about 10 to the minus 25 square centimeters. And let's see what are the signatures on cosmology. In the CMB, you see no sign at all. You need to look at the bottom plot. These are the residuals in the CMB power spectrum. Even if I crank up this interaction to the barn level, you see you get residuals at the 1% level, totally beyond cosmic variance. So you cannot see this. In the large scale structure, this is the meta power spectrum. You get residuals which are even smaller at the per mil level, okay, on linear scales. We can only trust this calculation up to K of roughly, somewhere around here before 10 to the minus 1 on linear scales. So the takeaway message is for linear cosmology, you can have a huge cross-section of scattering between dark energy and baryons, and it won't affect the observations. So this is in line with what I showed you in this nice diagram by Fergus. You can have large interactions between dark energy and electrons, which won't disrupt cosmology. But the real number is actually larger than 0.1. It's more like 10. That's why I say this number was actually wrong. Now, the question is, we can only trust our calculation on linear scales up to K roughly here. But what if we want to go to non-linear scales? Because maybe, most likely, we can get some interesting signatures there. So the only way to do this is to run n-body simulations. So that's what we're doing with my student Fulvio in Munich, and David Mota and Marco Baldi in Bologna, who is an expert on dark energy simulations. So we are running n-body simulations of scattering between dark energy and baryons. And we are finding these are very preliminary results, but our simulations show something interesting. So you see on linear scales, you get this very small suppression I showed you before, but on non-linear scales, this suppression becomes an enhancement, okay? And it becomes a huge enhancement of more than 100%. And we are still trying to understand this, but we believe it's due to the role of angular momentum due to the collapse of structure. So the point is, if you can reliably model non-linear scales up to this K, which I know people in this group are, of course, working on in the context of Bézier, Euclid, and so on, you can potentially try to look for the signatures. And this would be, if you cross-match these signatures with the ones on Earth, this could be a sign of dark energy talking to visible matter, if you can reliably model all the signatures. Let me just show you some snapshots of our simulations to show you how this really looks in the simulations. On the upper panel, this is a lambda CDM simulation. This is dark matter. If we take the equation of state to be in a quintessence regime, so above -1, and we crank up the cross-section to something unrealistic, like 100 times the Thomson cross-section, you see this leads to a suppression of power on large scales. You can see it in this zoom box. You see the structure is less clustered here. Now, remember, the sign of this extra force due to dark energy depends on 1 plus the equation of state. So if we take a phantom equation of state below -1, this suppression of power becomes an enhancement. So we get, you can see by eye, if you compare this box to this other one, structure is more strongly clustered over here in the phantom case than over here. So that's really what's going on very large scales. Okay, this is a scale of 10 H−megaparsec. So besides looking at the clustering of the large scale structure, we're also trying to understand other observations like halo mass function, density profiles, the baryon fraction profiles, and even systems like the bullet cluster. Because in this case, what you can get is you have a force between dark energy and baryons. So dark energy can direct the baryons, but not the dark matter. So the separation between the baryons, the gas, and the dark matter you see in systems like the bullet cluster is going to be affected by these interactions. This is all very preliminary work by my student, but we are seeing effects of up to 10% in these observations. So before I mentioned complementarity, so really, if we want to understand if dark energy is talking to visible matter, we need to really look at observations on different scales. On Earth, in these direct detection experiments, in cosmology, in the clustering of large-scale structure, and in astrophysics, and in these observations on galaxy scales. So I've finished the first part of my talk. Let me just give a quick recap, and then I'll see if there are any questions. So the takeaway message here is, I think there's a lot of potentially unharvested potential for directly detecting dark energy on Earth. And at the same time, we can look for complementary signatures in cosmology and astrophysics. And when you cross-match all of this together, perhaps we can get to the first convincing direct detection of dark energy beyond gravitational interactions in the next maybe 5 or 10 years. I'm very optimistic. I'll now move on to the second part, which is much, much more cosmological, and is how can we learn more about dark energy at early times this time, okay? In a way which is totally model agnostic. And I want to justify doing consistency test of lambda CDM, which I know is also something people in this group, especially in the past when Jose was here, have been interested in. And I will start from the Hubble tension, which is maybe the most clear and unclear at the same time sign of possible new physics. Now, there have been lots of models written which don't solve the Hubble tension. Many models every day. None of them works. So when I look at this from a very detached point of view, I think it's important to take a step back and look at this problem with different eyes. And the question I want to ask is, if we forget the Hubble tension, we must not forget that lambda CDM fits the data really well. So do we actually need new physics, okay? And this is the point of view people like, George Efstathiou have been advocating. And it's really important, I think, to understand why lambda CDM fits the data so well, because that can tell us where we need new physics, if any. And this motivates consistency test of lambda CDM. And let me provide a justified example for why we should do this at early times. So if we take the Hubble tension seriously, it appears to call for a substantial amount of early time new physics. Because if you want to solve the Hubble tension while not ruining the fit to BAO and supernovae data, what you need to do essentially is move the Planck contours, the blue contour over here, to the X spot, okay? And this requires lowering the sound horizon by about 7%. Now, it's not easy to do this because you need a lot of new physics to do this shift. This is a 5 sigma shift, roughly. And one way to do this is early dark energy. There's a huge debate as to how much it works. Now, what made me think is, one needs a lot of early dark energy around equality for this to work. One needs about 12% of the energy of the universe to be in this funny form of early dark energy. 12% is a huge number, okay? We are doing precision cosmology. The question is, why is there no clear sign of this funny new physics if I take the CMB data alone? Certainly, if there's so much new physics, you would expect to see it, right? And we don't, not in Planck. Maybe there are signatures of it in ACT, but I don't believe this, to be honest. So from my point of view, this motivates doing an early time consistency test of lambda CDM to understand why lambda CDM fits the CMB data extremely well. And this was something I published in a recent paper in PRD. And it's based on the so-called early ICCUB effect. So where does this come from? How to see this? This is the usual line of sight approach towards writing out CMB anisotropies, which people like Niels have been working to improve or to find alternatives to. But let me stick with this. It's the most used formalism. You can write out the different contributions to CMB anisotropies in terms of different physical effects. You have a Sachs-Wolf effect, which is the relative red shifting or blue shifting of CMB photons at the last scattering surface. You have a velocity term, a Doppler term. You have a polarization contribution, and you have an ISW, integrated Sachs-Wolf contribution. And this comes from the time variation of potentials at any time during the cosmic history. Now, you know that in a fully matter-dominated universe, your potentials are constant. These are your two Newtonian potentials, phi and psi. They appear in your perturbed line element in Newtonian gauge. And so you see, you can get only at two times you can get this contribution. You can get it at early times because the universe is not fully matter-dominated. So this is called the early ICCUB effect. It's generated around and shortly after a combination. And you can get it at late times because potentials again decay due to dark energy. And that's called the late ICCUB. Now, my point of view is very simple. If I'm going to put a lot of early dark energy at early times, this is inevitably going to affect the early ICCUB because it's going to change how your potentials decay. So let me do the most naive thing in the world. Let me take this term, the source term, and let me just do something very stupid. I put an amplitude in front. I call it AEISW. And I want to test whether this amplitude is consistent with 1. Because if it is, then it's a very good indication that the data is consistent with the lambda CDM prediction for the early ICCUB amplitude. Now, for those of you who are closer to the CMB side, this should look very familiar. It's totally analogous to A-lens. A-lens is a similar parameter which parameterizes the amount of lensing in the CMB temperature power spectrum. And it's known to be anomalous at about 2 sigma. It could be a fluctuation, but it's the reason why Planck data appears to prefer at face value a closed universe. Let's do something totally similar with the early ICCUB effect. If I try to constrain this number with Planck data, I get something which is totally consistent with 1. You see 0.988 plus or minus 0.027. And that's already a very important message. Another important question you can ask is, once I put in this new parameter, are any of my other 6 lambda CDM parameters shifting away to compensate for this? And the answer is no. The parameters which shift the most are the scalar spectral index and the baryon density, which shift by no more than 0.3 sigma, as you can see here. They move from the red contours to the blue contours. So the takeaway message is lambda CDM, like Planck data is totally consistent with the lambda CDM prediction for the early ICCUB effect. In fact, it's actually very slightly low, just below 1. One important example is early dark energy. Why does it work? Why does it seem to work, actually? It seems to work because you can fit the CMB data wonderfully well. As lambda CDM, you see residuals below the 10% level with a higher Hubble constant. But this comes at a very expensive price. The price is an increase in the dark matter density from 11% to 13%. It's a 20% increase. It's a huge increase. This has been argued to worsen the fit to large-scale structure data, either galaxy clustering, or simply you can see it as worsening the S8 tension. It's obvious. If I have more dark matter, it's going to give me more clustering at late times. So it's going to even raise S8 even more. The question is, why does early dark energy want this increase in the dark matter density? It's precisely because of the early ICCUB effect. So the way to see this is I take my CMB, I don't plot the full CMB spectrum, I plot only the early ICCUB term. And here you see, okay, if I take early dark energy with a low dark matter density, it's going to give me almost a 20% excess in the early ICCUB effect, excluded at like 5 sigma from my results. If I raise the dark matter density, it's going to give no more than 3 to 5% early ICCUB excess, which is totally in line with the results. You need to really construct designer models for the early universe. That's really the point. Either you pay the price and shift other parameters like the dark matter density, and then you ruin the fit to late time data. Or you have to really tune your early dark energy model to cancel this early ICCUB excess. So I mentioned that this increase in the dark matter density worsens the S8 tension. How do you see this? Well, one way to see this is what's the effect on the matter power spectrum? You see, if you take the best fit early dark energy model, this is the residual compared to lambda CDM in the matter power spectrum, matter, not galaxy. You see, you get an excess which increases on small scales, and you get up to a 30% excess in the wave numbers of interest to galaxy clustering surveys today, like BOSS. Now, when we stared at this with people in Cambridge, we thought, okay, this looks very similar to the suppression massive neutrinos give you except opposite in sign. So we gave a thesis to my master student, okay, throw in massive neutrinos in the picture and see if you can bring this residuals down to 0 in this purple range. The answer is naively, you can take a neutrino mass, which is very heavy, of 0.3 eV, okay, so well beyond what's allowed within lambda CDM, and you get these residuals, which you see within this wave number range are beautifully around 0, okay, so you would think that if you combine early dark energy with a non-zero neutrino mass, you could save these problems. You could save the day. It turns out the answer is actually no. This is all work in progress. First of all, because massive neutrinos actually worsen the SA tension even more because you are adding another dark matter component, essentially. It's negatively correlated with H0 in the CMB, and it's very, very hard to accommodate such a heavy neutrino in large-scale structure data. So you see, when we add massive neutrinos, our H0 posterior goes from the green curve to the red curve, so really no improvement at all. So the takeaway message is massive neutrinos don't solve the problems early dark energy faces with large-scale structure S8 or however you want to call it. Okay, I've finished the second part of my talk. Let me quickly highlight the results. The one takeaway message is that the CMB data from Planck is fit wonderfully well by lambda CDM. And it's very hard to raise the recombination, the expansion rate before recombination, like with early dark energy, and not mess up with the early ICCUB effect, which is very, very, very tightly constrained by Planck data. Okay, I'll move on to the final part. So you see sort of a trend. I'm interested in many things from particle physics to cosmology to astrophysics. The first part was very particle oriented. The second was completely cosmology. Let me jump a bit to astrophysics now and discuss different ways to search for light particles, which could be related to dark matter or dark energy or neither. I'm using dark energy in a very loose sense here. And these are based on black holes, shadows, and planets and asteroids. So what's a black hole shadow? I'm sure we've all seen this image. It was called the image of the century. So what you are seeing here, despite what popular media says, you are not seeing the event horizon of the black hole. What you are seeing is the gravitationally lensed image of the photon sphere. So the photon sphere is a region around the black hole where you can still travel on circular orbits, but these are unstable. So basically a photon here, if it's perturbed, it's going to have to make a decision. Either you scatter away or you fall onto the black hole. And this is the photon sphere. And when we image a black hole shadow, what we see is the photon sphere enlarged by gravitational lensing. Now for a Schwarzschild black hole, so a black hole which is non-rotating and uncharged, the size of the shadow is 3 times square root of 3 the mass of the black hole in gravitational units. Now one can ask the question, can we use this image, as rough as it is, to learn anything about fundamental physics? The answer is yes, because for the type of accretion flow, which we believe describes M87, which is the black hole we imaged here, the size of this dark region is independent to very good approximation of the accretion flow details. So in other words, there's the size of this dark region doesn't depend on gastrophysics, okay? So we can use this size to learn about fundamental physics. This is something I've been working on in the last 2 years or so. And we propose a very simple recipe, which is the following. Let's condense all the information in that shadow into 2 numbers. One is the diameter of the shadow, or more precisely, the distance to mass ratio. And this is roughly 11 plus or minus 1.5. And it's very consistent with a Schwarzschild black hole, because for Schwarzschild, this is 3 times square root of 3, which is 10.6, very close to 11. Another information is that the shadow is very circular. And you expect it to be non-circular the moment you move away from the curved black hole solution, okay? So you can use the fact that the circularity measured in some way is less than 10%, the deviation, to constrain deviations from the Kerr paradigm. And we've done many works on this. Let me discuss 2 interesting applications for scalar fields. Now, you might have heard about the black hole no-hair theorem, and it's the statement that black hole solutions in the couple Einstein-Maxwell theory are described at most by 3 hairs or 3 charges. the mass, the electric charge, and the angular momentum. And it's called no hair theorem because 3 is basically 0. Okay, if you have 3 hairs on your head, you're basically bald. Now, the moment you deviate from GR, you generally introduce other charges, new hair parameters, new parameters you need to describe your black hole. Let me discuss one very simple example. And this is where I couple the Einstein-Maxwell theory to a scalar field, which is conformally coupled to curvature. So this is a canonical scalar field, which has essentially a mass which depends on curvature. And this is a conformal coupling because this parameter 1/6 is the conformal value. Now, when you consider this theory, what you get is you get a 4th hair. The 4th hair, we call it S, it's a scalar hair. And it's essentially a conserved charge of the theory. And what we did in this paper was we compute black hole solutions in this theory. And then what we did is very simple. We look at how large is the shadow as a function of the scalar hair and the electric charge. And you can see it here. This gray region is the region allowed by observations. And the moment you change the electric charge or the scalar hair parameter, you see you quickly go out of this region. So that's one example of how you can constrain new scalar fields using the size of the black hole shadow. Let me discuss one example, which I think is even more interesting. And it's related to something called superradiance. So superradiance is a exponential enhancement mechanism, which works in the following way. If I have a certain black hole with a certain mass m, this black hole has a gravitational radius, which is essentially the size of the event horizon. If I have a light scalar field with a Compton wavelength roughly the size of the black hole, this scalar field can extract energy from the black hole in an exponentially amplified way. It's a runaway process. It's going to spin down the black hole and decrease its mass. Now, I glossed over this before, but the size of the black hole shadow depends on its mass and spin. So if I have a new light particle, which is sucking out mass and spin from my black hole, it's going to change the shadow. It's going to change the size of the shadow and how circular it is. The real question is, can we see this change on a human timescale? And in this recent paper with my student, which we are going to put out quite soon, we find that actually we can see observable changes in the black hole shadow size on human timescales, so of order 10 years, which means that if the Event Horizon Telescope look at their black holes over an extended period of time, they can potentially see the shadow changing in size if there are light particles around. What's the range of particle mass we can probe? Well, we can basically go down all the way to 10 to the minus 22 eV, which is fuzzy dark matter. So this is a potentially new way of looking for ultralight particles using black holes. And let me now discuss the very, very final thing in my talk, which is using instead planets and asteroids to look for ultralight particles. And the way it works is via precession. So we know that so GR leads to a precession, which was observed, for example, in Mercury almost 100 years ago. Now, if I have a new light particle, which could be a new light scalar or gauged vector field, what it's going to do is, okay, you can write down the effective Yukawa potential you get from this particle. And what this is going to do, if you do the full GR calculation, it's going to lead to a change in your precession from the GR value. I call it delta phi. Now, if we have objects for which this precession is very, very well measured, we can, of course, go and constrain the associated fifth force, the strength of the fifth force. So we did this in a recent paper using planets, the 9 planets of the solar system, actually 8, for which we measured their precession really well. And we took also 9 asteroids. These are dangerous asteroids in the sense that they are potentially hazardous for Earth due to their trajectories. And because they are dangerous, they are very well tracked with radar. And their precession is measured extremely well. And all the contributions to the precession from, say, Jupiter or Mars are very well modeled. And essentially, we can subtract these other contributions and constrain the strength of the fifth force. You can see our constraints here, making different assumptions. The interesting thing is that the tightest constraints on fifth forces in most of the range of the fifth force comes from torsion balance experiments. with planets and asteroids, we can actually get stronger constraints in a certain mass range over here, which is interesting for ultralight particles, of course. We are very close to the fuzzy dark matter regime. So this is something to look forward to in the future, especially because we've only taken 9 asteroids, but there are actually about 1 million of them. So if we can actually track them very well, we can improve these constraints by, even 2 or 3 orders of magnitude, potentially, if we can keep systematics under control. Okay, I've finally come to the end of my talk. I leave you with 2 plots from the first and second part. I hope I've convinced you overall that there's a lot of potential for looking for dark energy off the beaten track, beyond the standard cosmological searches for its gravitational interactions with standard cosmological probes. I think there's a lot to be done in the next 5 to 10 years. So I hope I really convinced you there are many more ways to look for dark energy than previously thought about. And I'll thank you for your attention, and I'm very happy to take any questions at this point.